We are going to investigate triangles a little bit more. Special triangles. A 30, 60, 90 triangle, because we're going to use it a lot, and a 45, 45, 90 triangle. And in particular, we are going to use these triangles when they have a hypotenuse of 1. Now, using trigonometry, I'd like you to find this side, which I'll consider x, because it's like a left-right distance, and this side, which I'll consider a y. Please find x and y using trigonometry. This is a right triangle. You may use SOHCAHTOA to find the missing side lengths.
Cody, can you give me one?
Come on, we can do it. A lot of us are just waiting, but that's not going to fly. Use SOHCAHTOA. It's a right triangle. I know you love the law of sines, but use SOHCAHTOA when it's easy to use. It's okay. Your calculator gives you very nice answers as well. Square root 3 over 2. It's a very nice answer that our calculator gives us. Thank you, calculator.
You want to try both of those?
I want you to find x and y, correct. Sine of the angle equals the ratio. So this equals opposite over hypotenuse. I like how some people are using 30 degrees. I like to use the bottom angles just because. The sine of 60 degrees equals y over 1. That's going to be simple. I just type in the sine of 60 into my calculator, and I get root 3 over 2. Then the cosine of my 60 degrees will equal the adjacent over the hypotenuse. That's easy because the hypotenuse is just 1. I just type in the cosine of 60 degrees, and I get the x is 1/2. Okay, let's find the side lengths x and y for a 45, 45, 90 degree right triangle. X and y will be the same. Why do you say that? Because the angles opposite of them are the same. It's an isosceles triangle. So understanding that the angles being the same, we just need to find one of them. So the cosine of 45 equals x over 1. Type in the cosine of 45 into your calculator, and your calculator tells you the nice number, root 2 over 2. So root 2 over 2 is x. Root 2 over 2 is y. We are going to use these triangles so often that we will commit them to memory. So we should be able to see for a 30, 60, 90 triangle with a hypotenuse 1. And we need to remember the side lengths. Now what's important, if we look back, we had 2 side lengths that were different. One side length that was 1/2 and a side length that was root 3 over 2. Sometimes it's like, I forgot which one goes where. But let's just analyze the number root 3 over 2 really quickly. Root 3 over 2. Changing that to a decimal, I can see that it's 0.866. Root 3 is bigger than 1, so root 3 over 2 is going to be bigger than 1/2. We are going to remember for the future, and for now, that when I have a 30, 60, 90 degree triangle, the longer side is the root 3 over 2 side. The shorter side is the 1/2 side. So depending on the orientation, understanding that the longer side is going to be opposite the bigger angle. So if that's 60 degrees, this must be 30 degrees. This is the longer side. The longer side is root 3 over 2. The shorter side is 1/2. If my 30, 60 degree triangle is oriented this way, where it's a shorter 30, 60, 90 triangle, well then the shorter side is here and the longer side is here. What's nice about 45, 45, 90 triangles is that it will always be oriented one way. We need to commit this to memory. These side lengths, especially for the 30, 60, 90. Because we will use those side lengths a lot moving forward. Okay, now what we could do is actually use our knowledge of these triangles to be able to find side lengths without using SOHCAHTOA. If I have a hypotenuse of x on a 30, 60, 90 triangle, the short side would be 1/2 x. Think about this being 1. If this is 1 and this is 1/2, well, if this is x, this must be 1/2 x. If this is x, pretend this is 1, well, the longer side is root 3 over 2. Well, the longer side must be root 3 over 2x. Now, what's cool about this is no matter what we're given, whether it's the shorter side length, the longer side length, or the hypotenuse, we can find the other two sides. Because if I want to go from 1/2 to root 3 over 2, what do I do to 1/2 to get to root 3 over 2? What operation, mathematical operation, can take 1/2 and turn it into root 3 over 2? I could, yeah, I could just multiply the 1/2 by root 3, and it turns into root 3 over 2. So if I'm given this side length, multiply it by root 3, and you'll have this side length. Going the other way around, if I have root 3 over 2, x, and I'm given this side length, and I want to find this side length, I can divide by root 3. Okay, let's look at if I'm given the long side. Or let's say I have the short side and I want to find the hypotenuse. What do I do to 1/2 to turn it into 1? Yeah, multiply by 2. And if I want to go the other way around, I would divide it by 2. The one tricky one is if I'm given the long side and I want to find the hypotenuse. Because to turn root 3 over 2x into just x, you're going to divide by root 3 over 2. I don't like to divide by root 3 over 2. I'd prefer to multiply by the reciprocal, 2 over root 3. Now again, it's the same as dividing by root 3 over 2. If I wanted to go the opposite way, if I have the hypotenuse, I'll just multiply by root 3 over 2. So we don't have to use SOHCAHTOA. I can just say this is a 30, 60, 90 triangle. This is one of the side lengths. Give me the other two side lengths. And you can be able to do it quickly, understanding that the hypotenuse is a ratio of 1 to the short side 1/2 to the longer side root 3 over 2. If this is x, this would be root 2 over 2x. This would be root 2 over 2x. To get from one of the side lengths to x, we would divide by root 2 over 2. That's the same as multiplying by 2 over root 2. If I could go from that way to the other way, well, it's just times by root 2 over 2. Let me show you what I mean by that. Here are two triangles, 30, 60, 90 triangles. Here's the taller 30, 60, 90 triangle. If I give you the short side's length 3, you can find the hypotenuse on the longer side very quickly. Let's think about it. If I went from 1/2 to 1, what do? Multiply by 2. Multiply by 2, that's got to be 6. If I go from 1/2 to root 3 over 2, what do? Multiply by root 3. Multiply by root 3, 3 root 3. Quick and easy, getting from one to the other. Okay? Now see if you could do it for this 30, 60, 90 triangle. Now understand we have a shorter length and a longer length. Opposite the 30 degrees, this is our shorter length. This is what we would consider the 1/2 length. The longer length would be considered the root 3 over 2 length. Find the other sides without using SOHCAHTOA. Yep, that's perfect. This being the hypotenuse being 1. How do I get from root 3 over 2 to 1/2? Divide by root 3. If I divide by root 3, this becomes 3 over root 3. You type that into your calculator, it tells you it's root 3. Well, watch what you can do. If you multiply the top and bottom and rationalize things, root 3 times root 3 is 3. 3 times root 3 is 3 root 3. The 3's cancel, giving you just root 3. I don't really care about rationalization. I don't want you to focus on it. Just focus on, I took this value, the root 3 over 2 side. I divided it by root 3 to get 1 over 2 divided by root 3. If I have the root 3 over 2 side and I wanted to turn it into 1, I could divide by root 3 over 2. So I could do 3 divided by root 3 over 2, but I'd rather multiply by the reciprocal 2 over root 3. So this would be 3 times the reciprocal 2 over root 3. And you get 6 over root 3, and I'm happy if you get that. If you type that into your calculator, rationalizes it for yourself when you do it. If, yes, you multiply the top and bottom by root 3 over root 3, it'd be 6 root 3 over 3, which turns into 2 root 3. Is that important? Not that important. A lot of math teachers say rationalization is very important, but it's not that important. They're the same, it's the same number. Just one has a square root in the bottom. Okay, let's see if you can figure out the side lengths for this 30, 60, 90 triangle if the hypotenuse is 3. And they should be nice and easy numbers. Now, recall, and this is important, this will be important moving forward, that the orientation of the 30, 60, 90 triangle is important. There's a shorter side and a longer side. The shorter side is opposite the smaller angle. This is our shorter side. Which of the two numbers, 1/2 or root 3 over 2, is the shorter side? 1/2. So this is the 1/2. This, therefore, is the longer side. This is the root 3 over 2. This is the hypotenuse. You can consider that length the 1 length. So how do you get from 1 to 1/2? Divide by 2. 1.5 or 3/2. How do you get from 1 to root 3 over 2? Multiply by root 3 over 2. So this is 3 root 3 over 2. How are we feeling? Not that bad, right? It all comes back to understanding the shorter side 1/2, the longer side root 3 over 2. Let's do this with a 45, 45, 90 triangle. And then we're going to watch a quick 5-minute video. It is. We'll talk about it. We'll talk about it. There are triangles that occur naturally inside circles. Oh my goodness. I thought we were doing trigonometry. Why are there circles? That's a good statement there. Okay, so this is probably the easier one. This is like the 1. Therefore, these sides are the root 2 over 2's. How do you get from 1 to root 2 over 2? You multiply by root 2 over 2. So this is 4 root 2 over 2. This is 4 root 2 over 2, or just 2 root 2. But if the side length is 4, that's the root 2 over 2. How do I get the hypotenuse, which is the 1? You could divide by root 2 over 2, but then you have like 4 divided by root 2 over 2. You could do that in your calculator. That's fine. I would like to, instead of dividing by a fraction, multiply by the reciprocal. So I would multiply by 2 over root 2. So this would be 4 times 2 over root 2, which is 8 over root 2, which ends up being 4 root 2. And your calculator does rationalize for you, but you can multiply the top and the bottom by root 2. That's 8 root 2 over 2, which is 4 root 2. Yeah, I'm fine if you leave it as 8 over root 2. Okay? All right, well, cool. We have those triangles down. We understand them. We are ready to recall the side lengths of a 30, 60, 90 triangle. The shorter leg being 1/2, the longer leg root 3 over 2, the hypotenuse 1. 45, 45, 90, shorter lengths, root 2 over 2. Well, we are going to, what appears to change gears. Okay, we're going to change gears and we're going to talk about a circle, a unit circle. What is a unit circle? It's a circle with a radius of 1. So this distance here is 1. This distance here is 1. The distance from the center to any point has a radius of 1. Okay, that's why we call it a unit. Unit, just 1 unit. Okay, now with angle measurements, we can actually look at the angle measurements of a circle. And we are used to talking about degrees and how there's 360 degrees in a circle. Well, what we're going to do, and this is just for this situation, we're going to call this a y-axis and this an x-axis. We're going to call this angle 0. And we are going to go around counterclockwise. That way we're kind of working in the first quadrant where everything is positive, the x's are positive and the y's are positive. So I'm going to say that this angle right here would be what? 90 degrees, right? If that's an angle. So up here I'm going to say this is 90 degrees. The angle right here created is 90 degrees. That means if I start here and go all the way to the other side, how many angles are we talking about? Okay, that's 180. This would be 270. And then if I go all the way around, 360 degrees are right back where I start, right? Now, I could also go in the opposite direction. In the counterclockwise direction, this is positive, or adding angles. In the opposite direction, we would be subtracting angles. So actually 270, I would also say is the same location as negative 90 degrees. If I went in this direction, I could say this is negative 90 degrees. Okay? We cool with that? All right. Now, why are we going counterclockwise? Again, because like this first quadrant is a beautiful quadrant. X's are positive, Y's are positive. But why are we using 360 degrees? Why are there 360 degrees in a circle? That's just how it is. That's a good answer. And that's actually the correct answer. There are 360 degrees in a circle because that's just how it is. It's actually a very arbitrary number. Why aren't there 100 degrees in a circle? Because that's not how it is. Let me show you a little video that will show you why they came up with the number 360. It's very interesting. I think you would like it. I have to go through the notes. All right, here we go.
Do you know why there are 360 degrees in a circle? Is it just a random number that was chosen? It could have easily been 100, 720, or anything else. Or is there a more logical reason behind it? There is no definitive answer to this question, but we do have a pretty good idea.
See, there's no definitive answer. Like Mr. Barber said, it just is.
360 is a number that is divisible by every number from 1 to 10, apart from 7. It actually has a total of 24 numbers that it divides into.
It's a lot of numbers.
This is a larger amount of dividing than any other positive whole number up to its own value.
So one reason is because you could divide 360 by a lot of numbers.
Highly composite numbers are good base numbers to perform common calculations with. But this still seems a bit too random to justify it as the number of degrees of a circle. We know that there are roughly 365 days in a year, but many ancient civilizations, like the Sumerians and Babylonians, had 360-day calendars. From their point of view, they were
nice, Mr. Smith.
stars that were of a fixed position in the sky. The sun would appear to move along an ecliptic path over the fixed stars for a duration of 360 days, moving 1 degree a day. The Sumerians and Babylonians also used the sexagesimal number system, which basically uses 60 as a base number when making calculations.
Instead of 100, we use 100 or 10. We use a base 10.
Just like
They use base 60.
It has 12 factors. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60.
It's a lot of numbers.
This makes it great for simplifying common calculations. Imagine it like this. Using 60 as a base number, you can half, quarter, and third it very easily. Half equals 30, a quarter equals 15, and a third equals 20. Nice round numbers. Now let's do it with 100. Half equals 50, a quarter equals 25, and a third equals 33.3 recurring. Sumerians and Babylonians worked out that day-to-day calculation would be much easier using 60 rather than 100 or any other relatively low number. If you took a circle and tried to fit an equilateral triangle inside it using the circle's radius, you could
Jason over iPod.
within the circle. Using the sexagesimal system, each would have a base value of 60, which multiplied by 6 is 360. So, putting these factors together,
This is good stuff.
we can say these are the most probable reasons why we have 360 degrees in a circle. Do you think this all adds up? Or
Do you think it all adds up? Well, guess what? We're not going to use degrees anymore because it's an arbitrary number. Forget about degrees. There aren't 360 degrees in a circle, okay? That's just some random number that they use. So we are instead going to use a different measurement for angles because this measurement is a true measurement. It is not something that is arbitrary. We are going to forget about degrees, they're gone. And we are going to use radians. Radians are a distance around a unit circle. Depending on how far you're looking. The distance around a circle with a radius 1. Now, what is the formula for the circumference of a circle? Does anybody remember from geometry? Circumference meaning distance around a circle. Pi r squared is the area of a circle. 2 pi r is correct. The circumference of a circle, or the distance around a circle, is 2 pi r. Well, that means if you have a radius of 1, the distance around a circle with radius 1 is 2 pi. So this is the distance around a circle with a radius of 1. So no longer are we going to say 360 degrees. 360 degrees will be equivalent to 2 pi radians. Going around an entire circle means I'm taking a distance starting from here, and I'm going to find this entire circle's distance with a radius of 1, and the entire circle's distance is 2 pi. It's also where we start. Starting here, 0 and 2 pi. Well, halfway around the circle, what you guys know is 180 degrees. What would be the distance around the circle that's just halfway around the circle? Just pi, right? Because you take 2 pi divided by 2 like you take 360 divided by 2. So all of a sudden, we are no longer going to use 180 degrees. We're going to say the distance around this unit circle, halfway around, is pi. Now, if I take 360 degrees and split it into quarters, I get 90 degrees, right? What would that be equal to in terms of a distance? Yeah, I could take 360 divide by 4, or I could take this 180 and divide by 2. Instead of going all the way around or halfway around, I'll do halfway to the halfway. So this distance here, we consider a pi over 2 distance. We're no longer going to be using 90 degrees. I'm going to say it's pi over 2. This is a true statement. These are true values. This is not arbitrary. This is not made up 360 because of the Sumerians or whatever. Okay? This is the exact distance around a circle with a radius 1. Okay? Great. Well, what would be 270? Right, I could add another pi over 2 to pi. You could consider pi as 2 pi over 2. If I add another pi over 2, all of a sudden I got 3 pi over 2. Right? Pi over 2, that's 90, plus another pi over 2, I get 2 pi over 2, plus another pi over 2, I get 3 pi over 2. So that would be the distance to the 270. What would be 30 degrees? $90 degrees divided by 2? 90 divided by 3. That would give me 30. Okay, so I like this. I like what we're thinking here. We're starting with 90 degrees, which we know is pi over 2, because we started with pi. And if I divide that by 3, pi over 2 divided by 3 is the same as times 1/3, pi over 6. So 30 degrees, pi over 6. I like how we're thinking about this. Starting with angles that we know. Okay, so if this is 30 degrees, what would be 60 degrees? Pi over 6 times 2, or pi over 6 plus pi over 6. So 2 pi over 6, right? I'm just adding another pi over 6. I get 2 pi over 6. We'll get there. So 30, 60, 90 degrees. We already said 90 degrees was pi over 2. But watch, if I add another pi over 6, I say, oh, that's 3 pi over 6, right? Well, that makes sense. That simplifies. Let's keep going around. So I'm at 90, then 120, then 150, then 180, right? Well, let's just add pi over 6s. 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. Oh, that's just pi. Okay, that makes sense. 7 pi over 6. Must be that angle there. 8 pi over 6 must be this angle over here. 9 pi over 6. Oh, does that simplify to 3 pi over 2? Okay, we know that. Good. 10 pi over 6. 11 pi over 6. 12 pi over 6. Remember, this is 0, but I'm also saying this is 12 pi over 6. Does that simplify? That simplifies to be 2 pi. All right, so let's start simplifying. We know that 9 pi over 6 is 3 pi over 2. I already simplified, and I need to zoom out a little bit. That's ridiculous. Did it really just disappear on me? Great, here we go. Ready? 0 pi over 6. Okay, you guys already wrote this down. 2 pi over 6 simplifies to be what? Pi over 3. 3 pi over 6 simplifies to be pi over 2. 4 pi over 6. Can you simplify 4 over 6? What's 4 over 6 simplified? 2 over 3. So this is 2 pi over 3. 5 pi over 6. Can you simplify 5 over 6? No. 6 pi over 6. You can simplify, that's pi. 7 pi over 6. Can you simplify 7 over 6? 8 over 6. Can you simplify 8 over 6? Oh, that's 4 pi over 3. 9 pi over 6. We simplified. 10 pi over 6. Can you simplify 10 over 6? 5/3. 11 pi over 6. 2 pi. Now, what's really cool with radians is the simplicity on these angle measurements based on a denominator. This pi over 6, how many degrees is it from this x-axis? 30. I'm saying just 30 degrees, just so we keep in mind the 30 degrees. This is just 30 degrees away. Now, if I go over to this 5 pi over 6, this ended up being at 150. 90, 120, 150. How many degrees away from the x-axis are you? Oh, this is 30 degrees too. This 7 pi over 6, how many degrees are you away from the x-axis? 30. 11 pi over 6, 30 degrees. Okay, what about the pi over 3s? What are they all away from the x-axis? They're all 60 degrees. What about the pi over 2s? 90. Okay, this is very important. All the blank pi over 3s give us 60-degree angles. in reference to the x-axis. All the blank pi over 6s gave us 30-degree angles from the x-axis. Okay, now let's talk about 45 degrees. We knew that 90 is the same as pi over 2. What would be a 45-degree angle? How do you get from 90 to 45? Divide by 2. So if I take pi over 2 and divide it by 2, what do I get? Pi over 4. So this is 45 degrees. If I add another 45 degrees, I get to 90 degrees, right? Well, if I add a pi over 4 to a pi over 4, I get 2 pi over 4s. Well, that's the same as pi over 2. I add another 45 degrees, 3 pi over 4. I add another 45 degrees, 4 pi over 4. Well, that's just pi. We know that. If I add another 45 degrees, 5 pi over 4. Another 45 degrees, I get to 6 pi over 4. That's 3 pi over 2. Look, we know that angle. That's 270. Then I add another pi over 4, I get 7 pi over 4. Add another 45 degrees, I end up at 8 pi over 4. We know that's 2 pi, or 0. Every single pi over 4 ends up being 45 degrees from the x-axis. Yep. Any number of pi over 4 when simplified gives us a 45-degree angle with the x-axis. So pi over 4. Pi over 4 is 45 degrees. So actually the distance around this unit circle, pi over 4 distance around a unit circle, is the same as a 45-degree angle measurement. Okay, now our goal is to be able to locate these angles so that we can do what we want to do next class without having to recreate the entire circle. Okay, so I'm not going to look back at the previous pages, but I'm going to be able to locate where 5 pi over 6 is, where 2 pi over 3 is, where 7 pi over 6, where 4 pi over 3, just like that. Here's how we're going to do it. First, I recall that if I have a 6 in the denominator, I'm how far away from the x-axis? 30 degrees. Okay, so this is giving me a hint that I'm 30 degrees away. So I have this angle, this angle, this angle, and this angle to choose from. How do I know which one is which? 5 pi over 6. Well, think about it. I know that pi is right here. Pi is the same as 6 pi over 6. Remember, when we go in this direction, we are adding. When we are going in this direction, we're subtracting. To get from 6 pi over 6 to 5 pi over 6, I would subtract a pi over 6. So I could say this is the same as 6 pi over 6 minus a pi over 6. Would I be going up to get to 5 pi over 6 or down to get to 5 pi over 6? Up, because I'm subtracting. So we have a winner. There is 5 pi over 6. It's 30 degrees away from the x-axis. It's 1 pi over 6, 130 degrees away from 6 pi over 6. 7 pi over 6, I would say, okay, the pi over 6. Don't pack up yet, we're not done. I would start with 6 pi over 6, and I'd add a pi over 6. Where does that place me? 6 pi over 6, add a pi over 6, I'm right here. That's 7 pi over 6, that location. If I have a pi over 3, I am saying a pi over 3 always makes what angle with the x-axis? No. 30, right? Pi over 6 was 30. Then add another pi over 6, I get 2 pi over 6. 30 plus 30 gives me 60. So I'm thinking, oh, that's a 60-degree reference angle. That limits me to these angles that are possible. Those are the 60-degree angles. Where's 2 pi over 3? Is it the first one? This is just 1 pi over 3. I would say, well, if I start at 3 pi over 3, subtract a 60-degree angle. Subtract a pi over 3. 3 pi over 3 is right here. Subtract a pi over 3, and I get here. That means 4 pi over 3 would be a 3 pi over 3 plus a pi over 3. That gets me right there. Pi over 6, right here. Pi over 3, right here. 11 pi over 6 is 1 pi over 6 away from 12 pi over 6. Start at 12 pi over 6. That's around the entire circle. Subtract a pi over 6, I get here. 5 pi over 3 is 1 pi over 3 away from 6 pi over 3. That gets me there. This is how we need to think about this. 3 pi over 4 is 1 pi over 4 away from 4 pi over 4. I subtract 1. Pi over 2. 5 pi over 4. 1 pi over 4 more than 4 pi over 4. We will be able to do this without creating the entire circle, and we will practice it before our next quiz. We will do these practice problems next class.